Okie doke. We've got example 2, apparently. Example 2 here, not exactly spelled right. The linear motion in this case is this rod going in and out, right? That's what they want us to find. The velocity and acceleration of the rod when the cam is at any position theta. So as this circle spins around, which by the way, it's not connected this time at point A, it's connected at point O, right? So uh, we've got to get a little bit creative with how we uh, come up with our relationship between this x displacement and the theta angular displacement. So they gave us a little bit of help here, though. They said, "Oh, look, you got this radius that you could relate with theta, but you could relate it to this x distance by using theta, right? So if you're looking at that, how do I relate s or x to theta? We can say this x is equal to the bottom two parts of the triangle, the bottom two sides, added together, right? Well, how long is the bottom of that triangle? That would be r cosine theta, if this is a right triangle here, which it is. So yeah, we could have two of those, two of the r cosine thetas, and that would give us the full length x. So from there, now we are just coming up with our calculus, right? We just got to make sure that we do our chain rule correctly. So let's see if we can do that here. If we started with x is 2r cosine theta, then we just got to make sure that as we go about with this one, this cosine theta, that theta is a function within the cosine function. So it's going to be giving us a chain rule there, right? So let's do the time derivatives of both sides, dx dt and d dt of 2r cosine theta. Right. So if we do dx dt, that's just going to be the velocity on that side. But d dt of this side, I've got a 2 and an r, which are constants, and then I've got cosine theta. That's going to turn into negative sine theta, right? Which if this was d d theta, that would be my derivative, but it's not, it's d dt. And theta is a function of time. So that means this is it's triggering a chain rule, right? So we did the outside function, now we need to multiply it by the derivative of the inside function, which would be theta dot, right? The time derivative of theta, which that is the same as our variable omega, right? The time derivative of theta. So we could rewrite that as negative 2r omega sine theta, right? Now let's do one more time derivative of both sides. See what we do. So this is going to turn into a, and the time derivative over here is going to be negative 2r, still a constant. Now I've got omega times sine theta, which are both functions of time. So I've got to make sure I product rule it this time. So product rule of omega sine theta would be the first times the derivative of the second, which would be cosine theta. But the derivative of sine theta is cosine theta, which triggered a chain rule. So that needs to be a theta dot, or instead of a theta dot, let's just put in omega, right? So that was the first times the derivative of the second, plus the second times the derivative of the first, which the derivative of omega would be alpha, right? And we could simplify that slightly, but that would basically be it. We could make this omega and omega, just an omega squared cosine theta plus alpha sine theta. And that just looks a little nicer. A little easier to plug our numbers into if we had them to solve. So that's it for that one. We could come up with some actual numbers if they give it to us, and we could say solve for the acceleration given a with a given angle theta and a given position s or something like that, right? So we can solve for a lot of them, and that's what we'll do in the next one.